Hi students, how are you all? Today's topic, continuation of current electricity. In the last class, we discussed about the series and parallel combination of cells. Actually, in the live class, I tried for the Kirchhoff laws, but it is not succeeded. That's why again I am recording and I will upload. Thank you for watching my lectures. Now I am going to continue today's topic, Kirchhoff laws. Right, this is very important for the CBSE exam. Okay, and now many times came in the exam, very important. Okay, and now Kirchhoff laws, there are two laws are there. Kirchhoff laws are two are there. What are they? And Kirchhoff is the name of the scientist. He gave the two laws, and that two laws are the first law and the second law. The first law is also called as junction law or the current law. What is junction law? First law is called as junction law or the current law. Okay, the first law is that at any junction, the sum of currents entering the junction is equal to the sum of currents leaving from the junction. At any junction, sum of currents entering the junction is equal to the sum of currents leaving from the junction. That means how much current enters toward the junction, that much current leaves from the junction. What is a junction? If two or three wires meeting at a particular point, that point is called as junction. Look at here this diagram. There are some wires are there. 1, 2, 3, 4 wires are there. Okay, this is the resistance. Each wire has some resistance, that indication. And now these 4 wires are meeting at this point, and now this point is said to be junction. This point is the junction. Okay, this point is the junction, where J is the junction. Right. Now at the junction, what is the rule? The rule is that the sum of currents entering into the junction. Here the current is entering. Here the current is entering. That means I1 and I2 are entering, and from the junction which are leaving, I3 is leaving and I4 is leaving. And by the arrow mark we know that arrow mark is towards the junction means that is entering, and arrow mark is away from the junction means that are leaving. What is our first law? The first law is that the sum of currents enters equal to the sum of currents leaves from the junction. Look at here. What are the currents enters towards the junction? From the figure you can tell. Right, it was very simple. That is I1 and I2 are entering. Then the sum of currents is I1 plus I2. Then the sum of currents leaves from the junction. I3 is leaving and I4 is leaving. Then we write I3 plus I4. Okay, and this we can also write like this, I1 plus I2. We will take this I3 to left side. Then we will get minus I3 and minus I4 is equal to, we will get as 0. Then this we can also write like this, that is I1 plus I2 plus minus I3 and plus minus I4 we can write is equal to 0. Okay, what I did it here, the sum of currents entering equal to sum of current leaves from the junction. That formula I used. By using that we wrote this equation. Okay, and now let us see, this we can also write like this. From this we write one thing, that this is the sum of all currents at a junction is equal to 0. This we can write as summation. Summation of currents is equal to 0. This we can write as like this, that is algebraic sum of currents. Algebraic sum of currents. Okay, here this is the sum of currents. Sum of currents equal to 0. Algebraic sum of currents at any junction is equal to 0. We can also give the Kirchhoff first law like this. Algebraic sum of currents at any junction is equal to 0. We can write. But when you write the sum, at that moment the entering currents we have to take as, in this entering currents I1, I2 are entering, okay, that are we can take as positive, and the leaving currents we can take as negative. That we have to note. This is about first law. It was very simple. how sum of currents entering into the junction equal to the sum of currents leaving from the junction. Okay, and now let us see the second law. The second law is that the second law is also said to be the loop law or the voltage law. Okay, and second law, Kirchhoff's second law, is said to be loop law, or it is also said to be voltage law. Okay, very carefully you have to hear. Okay, and now the second law is or the voltage law. What is second law or the voltage law? That is, it was very simple. It is applicable for the loop. What is a loop? For example, this is a cell and this is a resistance, and now any closed circuit is said to be, this is a closed circuit, and now that is said to be loop. Okay, where you started, for example, this is A, B, C, D, A. Okay, the current starts like this and goes like this, and now we check A, B, C, D, A is a loop. You started at A and again going towards the B, and next C, next D, next A. This is a loop. And you can also take like this, you can travel like this. At that moment you take the loop. You started from A, right, and going to D, and the next going to C, next going to B, next going to A. Then this is also one loop, right, like this. This is said to be loop. Loop is a closed circuit or the closed path. Okay, loop is a closed path. Now for the closed path we can apply this law. That's why this law is called as loop law. Now what is the statement of this loop law? It was very simple. That is algebraic sum means addition, not SOME. Okay, algebraic sum of potential differences. Algebraic sum of potential differences. Algebraic sum of potential differences are potential differences and EMFs in a closed circuit, in a closed path involving, or simply in a closed path, is equal to 0. We write is equal to 0. Right, what I am telling it here? Algebraic sum of potential differences and EMFs. Algebraic sum of potential differences, sigma V. Algebraic sum of EMFs, sigma E. Sigma indicates, this sigma indicates algebraic. So, algebraic sum of, okay, sigma potential difference, algebraic sum of EMFs is equal to 0. This is second law. What is our second law? Algebraic sum of potential differences and EMFs in a closed path or the closed circuit. Closed circuit or the closed path is equal to 0. Okay, sum of potential differences equal to 0. This is our second law. Now let us see. Let us try to apply for this second law at some places, and for to apply the second law, actually we require some sign convention rules. Now I am going to explain the sign convention rules for this. Okay, the sign convention rules is, this simply some books it may be given as algebraic sum of potential differences also equal to 0. We can write direct. We can also write like this. This simply also we can write algebraic sum of potential differences is equal to 0. This is also correct statement. Okay, we cannot involve the EMFs, but because EMF is also potential difference, right? Okay, now sign convention rules we have to use. Okay, the first sign convention rule is, okay, when you are going to across the closed path, for example, this is a cell, and now it has a EMF E, and this is a resistance R1, and the next this is R2, and next this is R3. Okay, now look at here, the current direction is what? What is the direction of the current? Current flows from positive terminal of battery to negative terminal, right? Current flows like this. This is the direction of the current, right? And now here the current flows from this point to this point, right? For example, this is A, this is B, C, D. Current flows from A to B, next B to C, C to D, right? That means here current, actually we know that the current flows from high potential to low potential. That means at point A the potential is more, at point B the potential is less. Okay, that means current flows from high potential to low potential. You have to remember. Okay, I may select the path like this. In the closed path you may travel from A to B, B to C, C to D, D to A. Like this we can select the path. Okay, the first path we can take one closed path. I will take closed path. Okay, the path 1 I will take like this. Okay, I started at A and goes to B, next to C, next D, next A to B, B to C, C to D, A to B, B to C, C to D, D to A to B to C to D to A. This is the one closed path. I will select this another closed path like this in the reverse. Like this, I started from A and goes to D, next goes to C, next goes to B, next goes to A. Okay, started at A and goes like this, like this, like this, like this, and again come back to A. Right? And this is path 1 and this is path 2. I am traveling. In any direction you travel, right? Okay. Let us see first. While traveling and while applying the algebraic sum of potential differences in a closed path is equal to 0, then you have to use some sign convention rules. Then what are the sign convention rules? Okay, now while traveling, the first rule is that is if you travel in the direction of the current. Okay, for example, you are traveling in the direction of the current. Okay, in the direction of the current means A to B, B to C, C to D, D to A. It is in the direction of the current. If you travel in the direction of the current, right, then at that moment potential difference across the resistance we have to take as negative. This is first sign convention rules, and vice versa. That means if you travel opposite to the direction of the current, then you have to take it as positive. Okay, now first rule is that if we travel in the direction of current, okay, this law is very important, and note it properly. Okay, and listen very carefully. Okay, sign convention rules are very important. Without sign convention we cannot apply anything, right? If we travel in the direction of current, okay, potential difference across resistance is taken as negative. Potential difference is taken as negative. Okay, I will explain, and after listening all sign convention rules, by taking one example how to apply these rules, that I will tell. Then you will get full clarity after explanation of total sign convention rules along with example. Okay, now take the screenshot and note the points. And now the point is that the next thing is that what I am going to tell. The first one is what? If we travel in the direction of the current, the potential difference, you may travel in the direction of the current, you may travel opposite direction of current. That is your wish in the closed path. Okay, you may select the path 1, path 2. Previously example I said, either you may select the path in the direction of the current, or you may select the path opposite the direction of the current. Then let us see in the first example what I am telling it here. This is if we travel in the direction of the current. Okay, this is the resistance. Okay, this is point A and this is point B. For example, the current flows at point A, the potential is VA, and at point B the potential is VB. and the current flows from A to B, and we are moving from, the current flows from A to B like this. Okay, current flows from A to B. I am selecting the path that I am moving from A to B, right? That means I am going in the direction of the current. You may go this side or you may go this side. Okay, where you will go, why, how you will go, with example you will understood, right? First listen the rules and later you can apply the rules, right? And look at here, this is resistance. What I am doing it here, this is the direction of the current. Direction of current I am taking example, whatever it may be the direction of the current. First if I am taking the right side. Okay, here the current flows from high potential to low potential. That means we write from this VA greater than VB, right? VA greater than VB. Then potential difference, that is V is equal to, we have to take as negative. Okay, we have to take as negative. Potential difference, what you have to take? Negative. That's value is minus IR. We have to take it as V is equal to minus IR. Potential difference we have to take negative. Why we have to take potential difference negative? The potential difference is nothing but V. Here the V is nothing but VB minus VA, right? Final potential minus initial potential. When you do VB minus VB, VB is less minus more, you will get automatically negative. You have to take negative. Okay, this is the first rule. And in the same thing, if we travel opposite to the direction of current, if we travel opposite to the direction of current, then potential difference across resistor is taken as positive. This is the second sign convention rules in the first point. In the second point, in the first point there are 2 points are there. Okay, if we travel in the direction of the current, then the potential difference can be taken as negative. If we travel opposite direction of current, then we have to take positive. Look at here the same diagram. Okay, and now the diagram is that I will explain. First listen the rules. Okay, and this is the resistance, right? This is the resistance. Now I am moving from A to B. This point A potential is VA, at point B the potential is V. This is A point and this is B point. For example, the direction of the current is right side. The current flows right side. I am also moving right side. Okay, what I am doing it here, this case is completed already. Okay, we are going in the direction of the current. Now next we are going opposite direction of current. Look at here. Okay, right. And then at that moment what happens at here? Okay, how to write this one, these all things. Okay, the same thing that current flows from A to B, the same diagram I said. That means current flows from high potential to low potential. That means here potential is more, here potential is less. Then potential difference is there at here, VA greater than VB. Okay, then the potential difference is what? Potential difference. Okay, and potential difference we write as potential difference V we write as VB minus VA. Here we are telling that VA greater than VB. Okay, potential difference is VB minus VA, but we are traveling from B to A. Okay, when you travel from B to A, B is initial, A is final, then here we write the potential difference as VA minus VB. Why we will write like this? Here we are traveling from B to A here. Okay, travel from B to A. B is initial and A is final. Here we are traveling from A to B. A is initial, B is final. Potential difference is final minus initial. Okay, here also potential difference is final minus initial we have to take. We are traveling from B to A. This arrow mark is this like this there. Opposite direction of current. Here VA greater, VB less. Then we will take as positive, right? This is positive. Potential difference is positive. Potential difference we have to take as positive. That is plus IR. plus IR. Okay, right, potential difference according to Ohm's law, it is IR. These are the sign convention rules. It was very simple. If we go in the direction of travel, in the direction of current, if we go in the direction of current, potential difference is negative. Why? Current flows from high potential to low potential. High to low you are going. You are going in the direction of current, means high to low you are going. Potential difference, low minus high, negative you will get. Here we are going opposite direction of current, right? We are going opposite direction of current. That means here like this we are going. That means low to high we are going, right? This is high, and this is low, right? If you go low to high you are going, means potential difference high minus low gives positive. Here you are going high to low, right? When you go from high to low, the potential difference is low minus high, it will gives negative. When you go from low to high, right, it was very simple. I will tell. For example, this is the resistance, okay, and here the current direction is this one. Here 20 volt is there, here 5 volt is there, right? Now I am going from A to B, okay, A to B. What is the potential difference? What is the potential difference? I am going in the direction of current direction I am going. Potential difference is what? I am going from A to B. A to B means in the direction of current, right? When you go from A to B, the potential difference is 5 minus 20. 5 minus 20 gives minus 15. That means potential difference is negative. Potential difference is negative, right? Potential difference is negative. The same diagram, for example, you are going from B to A. B to A you are going. B to A you are going means opposite direction of current is going. Current goes right side. B to A you are going. Okay. B to A you are going means potential difference is what? B to A you are going. Final is this one. Initial is this one. Initial. Then final minus initial we have to write. Final minus initial. What is the final? We are going from B to A. Right. Final is 20. 20 minus 5. We will get plus 15. Right. That means, okay, when you go from A to B, high to low you are going. Then potential difference 5 minus 20 negative you will get. When you go from B to A, final minus initial, right? 20 minus 5, it will give 15 volts. Look at here. A to B you are going. Final minus initial 5 minus 20 minus 15. B to A you are going. B to A you are going. Final minus initial 20 minus 5, right? Where you started, that is initial. Where you ended the journey, that is final. Potential difference we have to take as final point minus initial point. Okay, right? Potential difference may be positive or may be negative. That is, if you travel in the direction of the current, then we have to take as positive, and if you travel opposite direction of current, we have to take as negative. Okay. Now let us go for the cell. Okay, sign convention rule for the resistor is completed. Now cell I am going to explain. Okay, look at here. This is the first point, is very important. Okay, now the second point is that sign convention rule, second point. Very important. I am explaining very slowly and listen very carefully. And the third point is that, second point. Okay. And in the closed circuit, this is the across the resistance law or sign convention I gave. And now I am going to tell the across the cell. Okay, across the cell. And across the cell or capacitor, if you want to know the potential difference, right? Across the cell or capacitor, we will not consider the direction of current while measuring potential difference. Remember that? Okay, across the cell or capacitor, okay, if you want to find out the potential difference, at that moment we cannot consider the direction of current across the cell or capacitor. We will not consider the direction of current while measuring potential difference. What we will have considered, okay, that is the first point is that if we travel from positive terminal of battery to its negative terminal, then EMF across the cell, EMF is also potential difference, across the cell is taken as negative. EMF or potential difference, both are same. Okay, potential difference is taken as negative. Example I will tell. Okay, this is the cell. Okay, this is point A and this is point B. Whatever it may be the direction of the current, its EMF we can take as E. Now this is the positive terminal and this is the negative terminal. I am traveling from positive to negative, A to B, right? When you travel from positive to negative, positive is high potential, negative is low potential, high to low I am traveling. Then potential difference, what happens? Final minus initial, low minus high, negative is low and positive is high, low minus high, potential difference is negative we are getting, right? Here the potential difference you have to take as negative. Potential difference, okay, V is equal, we have to take as negative. This potential difference here is equal to EMF. Okay, potential difference is equal to EMF of cell. And the next, in this B point I will tell again in the second one. If we travel from negative terminal of battery to positive terminal of battery, right? If we travel from negative terminal of battery to its positive terminal, then EMF or the potential difference across the cell is taken as positive. Okay, right. And example is, this is the positive terminal of the cell, negative terminal of the cell, this is A and this is B. Okay, now this is the positive terminal and this is negative terminal. Now I want to go from B to A, right? I am selecting the path from B to A. When you go from B to A, that means you are going from negative to positive, low to high. Negative is the low potential, positive is the high potential. Low to high you are going. Potential difference, what happens? Potential difference is the final minus initial. You are going from B to A, that means low to high, high minus low, potential difference gives the positive, right? The potential difference V we can take as positive. This potential difference is equal to plus EMF, right? EMF of cell we have to take as positive. And the next, let us see one example based on this. Okay, it was very simple. By simplifying, in one time we will tell these all sign convention rules. Okay, that is, in one word we can tell the potential sign convention rules, right? By the conclusion, right? The conclusion is that potential drop can be taken as while traveling in the closed path. The potential drop can be taken as negative and potential rise can be taken as positive. Okay. Sign convention rules. Simply above sign convention rules, we can express in one line. We can express in one line. Okay, we can express in one line that simply above sign convention rules you can express in one line, that is potential drop can be taken as, drop means decrease. Okay, potential drop can be taken as negative, and potential rise can be taken as positive, right? That's all. Rise means increase, potential rise can be taken as positive. Okay, potential rise can be taken as positive, can be taken as positive. That means drop means decrease in potential can be taken as negative, increase in potential can be taken as positive. These are the sign convention rules. Now, how to apply these sign convention rules for certain place? What is the need of these Kirchhoff laws? The Kirchhoff laws are used to find out the direction of the current, and also used to find out the current magnitude in different branches in complex circuits. In simple circuits we can find out the current by using Ohm's law, but in complex circuits we can find out the currents by using Kirchhoff laws, and Kirchhoff laws are the simple to find out the current. Let us see next one example. Okay, we will apply the sign convention rules. Listen very carefully, it was very important. Okay, you may confuse, that's why listen very carefully and don't miss, and don't forward the video. Okay, and clearly you have to listen. This is the cell, the first EMF E1, and this is the resistance R1, and this is the resistance R2, and this is the resistance R3. Now in this, for example, if you want to find out the current, find the current in the circuit. Find the current in the circuit. This is our question. We have to find out the current in the circuit. Okay, let us see how to find out the current in this circuit. For that, we have to take the direction of the current like this, from positive terminal to negative terminal, like this. This is the direction of the current. Current flows. Take one closed path, and for that we have to take one loop. This is A, B, C, D. Okay. Now one loop I will take. Second law I want to apply the loop law. Okay, loop law. Okay, I will take the loop. First I will take the loop as closed path, closed loop. Okay, according to Kirchhoff's second law. Okay, according to Kirchhoff's second law, we can apply the Kirchhoff's second law. According to Kirchhoff's second law. Okay, what is our second law? And for the loop, second law we can write loop. For the loop, we will select the loop. It is a loop law. A, B, C, D, A is one loop we can select. Or otherwise A, D, C, B, A. One loop we can select in the direction of the current. Or other loop we can select opposite direction of current. Any one you can select. Your wish, in any way we can travel, right? Let us, for example, we want to travel from in the loop that is A, B, C, D, A. I want to travel from A to B, next B to C, C to D, D to A. In this loop, I want to apply the Kirchhoff's second law, right? Now, what is our Kirchhoff's second law? Algebraic sum of potential differences and EMFs equal to 0. Simply we write algebraic sum of potential differences equal to 0. No need to tell the EMF, because EMF is also potential difference, right? Okay. Algebraic sum of potential differences is equal to 0. What are the potential differences? First, we have how to find out. Very carefully you have to listen. A to B I am traveling. Loop I am selecting A to B, B to C, C to D, D to A. You may select like this: A to D, D to C, C to B, B to A. Okay, let us see. Second law is algebraic sum of potential difference equal to 0. We have to apply the sign convention rules. First I am traveling from A to B. Listen very carefully. A to B I am traveling. When you travel from A to B, right, I am going in the direction of the current, right? A to B I am traveling. Look at here, I am traveling from in the direction of current. Like this I am traveling. This is the path I am selecting. This is the path I am selecting. Okay, that means in this path, what I am doing it here, I am going in the direction of current A to B. Current is downward. Right, when you go in the direction of the current, what happens? Potential difference you have to take negative. High potential, low potential. Potential drop occurs. That's why we have to take negative. Negative, what is the potential difference across the AB? When you go from A to B, potential difference is IR according to Ohm's law. IR1 minus IR1 is the solution. Okay, and potential difference is minus IR1. Okay, why we are taking the minus? Because you are going in the direction of the current. That is the sign convention, first point. And next, B to C I am traveling. A to B completed. B to C. B to C also I am going in the direction of the current. Current is right side, already arrow mark they give. Arrow mark current direction kaise diya hua? How we gave the current direction? Because current flows from positive terminal to negative terminal. And the next B to C I am taking, that is minus IR2 we will write. Because again we are going in the direction of the current. If you go in the direction of the current across the resistance, potential difference you have to take as negative. Okay, I will revise the sign convention rules once. Okay, this is the resistance. Okay, current travel. You travel in the direction of the current, potential difference you have to take negative. This is the resistor. If you travel opposite direction of the current, current right side, then potential difference you have to take positive. Okay, this is the cell. When you go from positive terminal to negative terminal, right, then potential difference we have to take as negative. When you go from negative to positive, we have to take as positive, right? When you go from positive terminal to negative terminal, right, potential difference is negative, minus EMF. Negative to positive, then positive, right? And here in the direction of the current negative, opposite direction of the current positive. These are the simple rules, right? And now we have to apply these rules at here, sign convention rules. Okay, and then in the coming soon classes, this totally we will use. That's why I am explaining very slowly. And next, B to C I in the direction of current I am traveling, then that is also we will take as negative, minus IR2. Next, C to D, B to C completed. C to D. C to D also in the direction of the current I am traveling, minus IR3. Next, D to A I am traveling. D to A, when travel from D to A, there is no resistance at here. What is there here? Cell is there. Across the cell, don't go for the direction of the current. What we have to do? You have to check whether you are going from negative terminal to positive terminal or positive terminal to negative terminal. In case of the cell, across the cell, second rule is that, then don't consider the direction of the current. If you travel from positive terminal of the battery to negative terminal, then you have to take potential difference as negative. Look at here. I am traveling from where to where? D to A. A to B completed, B to C completed, C to D completed, D to A I am traveling from, that means negative to positive I am traveling, then we have to take positive. When you travel from negative terminal of battery to positive terminal, negative to positive, look at here, arrow mark is given left side, that means I am traveling from negative to positive, then you have to take positive, right? Then that is positive EMF plus E is equal to 0. Right, completed. This is the sum of potential differences in a closed circuit. This is the sum of potential differences and EMFs across a closed circuit. In a closed circuit, that is equal to 0, right? Equal to 0 I kept. Then next I will simplify like this. E is equal, we will get as IR1 plus IR2 plus IR3 we write. Then I is common it here on the right side, then we will get R1 plus R2 plus R3 we will write. Then I want to find out the I, current in the circuit, right? Our question is to find out the current. Then current formula we will get as E by R1 plus R2 plus R3, right? Okay, like this we can find out the current in the circuit by applying the Kirchhoff law, right? This is the Kirchhoff law, how to apply the Kirchhoff law. Have you understood? Right, algebraic sum of potential differences in a closed circuit, we have to take it as 0. Next, let us see one more example for this. I will give the one more example. Okay, I am going to rub by pressing the pause, right? It will save the 1 minute. Okay, look at here. This is our question. The next question is that one closed circuit they gave with two cells, right? With two cells, first cell EMF E1, second cell EMF E2, first cell internal resistance, this resistance is inside the cell, that is R1, second cell internal resistance is R2, that is also inside the cell. And now here what we are telling it here, when you connect these two cells I shown in the figure and I connect it to the external resistance capital R, question is that find the, if E2 greater than E1, if E2 greater than E1, right, EMF of second cell is greater than EMF of first cell, then find the current through the resistance capital R. This is our question. How to find the solution for this? To find the solution, first we have to draw the direction of the current. To draw the direction of the current, right, okay, note a cell whose EMF is much greater, right, then from that the current will starts. Okay, here E2 is greater than, then this current will discharge. Large EMF cell will discharge and the low EMF cell can charge. In this, E2 will discharge and E1 will charge. Why? E2 is high EMF. Okay, it will discharge. This is the positive terminal and this is negative terminal. This is the negative terminal, this is positive terminal. Look at here, negative connected to negative. This is not the correct combination of series. Right? In the series combination, positive terminal of first cell connected to the negative terminal of second cell. And look at here, current starts like this and goes like this. What happening at here? The first cell is discharging from the current, from the second cell current is coming like this, and current enters into the first cell. That means what happening? Actually, from the positive of the cell, current should be come outside, but it is not coming out, it is entering into the cell. That means what? Here the second cell is discharging, second cell is discharging, second cell is discharging, right, and the first cell is charging, and first cell is charging, right. This is our case, and I want to find out the current in the circuit. For that we have to select the loop, anyone you can select. Okay, in the direction of current I am selecting like this, A, B, C, D, any loop you can select. You can select opposite and again find out, you will get the same value. Okay, then the loop, I am selecting the loop. Okay, according to Kirchhoff's second law, according to Kirchhoff's second law, right, what we know? Algebraic sum of potential differences equal to 0. Algebraic sum of potential differences equal to 0. Okay, sigma V equal to 0. Then we will select the loop for this. Loop is, I will select the loop, that is loop A, B, C, D, A. I will select A, B, C, D, A. I will select. Then start the applying the law. Okay, algebraic sum of potential differences equal to 0. Let us start from A to B. You are traveling. Okay, first A to B I am traveling. When you go from A to B, first we got cell. When the cell comes, then what you have to check? Whether you are traveling from positive to negative or negative to positive, that you have to check. If you travel from positive terminal of cell to negative terminal, don't bother about the direction of the current when you will go from across the cell, right? If you go from positive terminal of cell to negative terminal, then the potential difference is equal to EMF at here. Okay, and that EMF you have to take as negative, because you are going from positive to negative, means you have to take as negative. That is according to sign convention rules. Minus E1. Next, resistance came here. Resistance, current is I at here. When you going across the resistance, you have to bother about the direction of the current. You are going from A to B, right side you are going. Current also going right side. That means you in the direction of current you are going. Right. At that moment, if you go in the direction of the current, you have to take potential difference. You have to take as negative. Minus IR1 we have to take. And next, I am going from negative terminal to positive terminal. A to B I have to travel. In the middle there are so many are there. Right, negative to positive you are traveling. When you go from negative terminal of first cell to positive terminal, then the EMF you have to take as plus C2. Right. When you go from negative to positive, A to B I am traveling. First I travel from positive to negative of the cell, then minus we have to take. Negative to positive you are traveling, plus you have to take. Okay, while traveling in the closed path, if cell comes, Then cell across, you have to check whether you are going from positive terminal of cell to negative terminal or negative to positive. Then next, negative to positive plus C2 I get. Then again I am going across the resistance. Then minus IR2 we have to take, minus IR2, that is equal to, that is minus IR2 why we have to take, we are going in the direction of the current, right? Okay, and minus IR2 we have to write. Then next, across BC, across BC there is no resistance, conductor wire, potential difference is 0 because current into potential difference is current into resistance, but BC is a conductor, resistance is 0, we write potential difference is 0. Across BC nothing is there. Next is across CD we have to travel. When you go from C to D, right, in the direction of A to B completed, B to C completed, C to D. B to C there is no potential difference. C to D, C to D in the direction of current I am going. Current is going from C to D. I am also going, selecting the path loop C to D, right, A to B, B to C, C to D, D to A. I am traveling like this, A, B, C, D, A loop. I am selecting A, B, C, D, A loop means I am traveling from A to B, B to C, C to D, D to A. This is the loop. Okay, I am traveling like this, right? And then next, in the C to D I am traveling, that means in the direction of current I am going. In the direction of current, if you will go across the resistance, then you have to take negative, right, minus IR. Then D to A, no potential difference because conductor. Then finally A to B completed, B to C completed, C to D completed, D to A also completed. Then finally reached to the same point A. Then algebraic sum of potential differences. These are the algebraic sum of potential differences across the closed path. Okay, that is equal to 0 we have to write. Okay, then we have to simplify this. This minus E1 minus IR1 minus IR2 minus IR we can take to right side. Okay, if you will take them to right side, then what you will get? This is minus E1 plus E2 is equal to IR1 plus IR2 plus IR. I is, this we write as E2 minus E1 is equal to, I is common it here, we write capital R plus R1 plus R2, right? Then here we can find out the current. Then the current is E2 minus E1 by capital R plus R1 plus R2. This is the current in the circuit. Okay, like this we have to find out the current. And without using Kirchhoff laws, previously I said one formula, that is the current is equal to effective EMF by effective resistance. Effective EMF is what? In this, these two are appearing series but wrong connection. Negative connected to negative. In the effective EMF is what? E2 minus E1 in the wrong connection. Effective EMF by effective resistance is what? This is only one way. That means all are in the series. Then R1, R2, capital R. Effective resistance is what? Capital R plus R1 plus R2, because in series combination we have to add. That means current is equal to effective EMF by effective resistance. Direct also we can write the formula. Effective EMF is E2 minus E1 because the two cells are connected wrongly, right? And the series, you know, wrongly series I gave in the note. And effective resistance in the series combination is capital R plus R1 plus R2. This is how to apply the Kirchhoff's second law. And the next, I am going to give one example for the Kirchhoff's first law. For that I am going to rub by pressing the pause button. Okay, look at here. This is our next question. That figure shows three resistors. Figure shows three resistors. 1, 2, 3. Are connected with switch S. This is the switch S. Are connected with switch S. Initially the switch is open. This is open now. When the switch is closed, find the current passed through the switch. Then when we close this switch, how much current passes through the switch? This is our question. And it was very simple to find out. Let us see. This is 20 volt they gave in the diagram. This is the resistance R1 we will write. Okay, this is R2. And this we write as R3, right? Okay, this is R2. And this is R1. And the current direction, let us give, the current goes from high potential to low potential. By mistake, if you will give the opposite direction, okay, direction of current wrongly, then there is no problem. Current flows from high potential to low potential, 20 to 5, right? This is 20 volts, this is 5 volt, this is grounded 0 volt. Current flows from high potential to low potential. This is high, this is low. Current goes right side. This is high, this is low. Current goes this side. That means current started from here. That is, for example, I1 it is coming, okay, I1. And after coming to this point, the current will be divides. The part of current goes this side. That is I2. And the part of current goes this side. That is I3. In our question, they are asking to find out the I3 when the switch S is closed. What is I3? Then for that, from the Kirchhoffs first law we write, from Kirchhoffs first law. What is our Kirchhoffs first law? Junction law. At the junction, entering current equal to leaving current. What is the entering current for this junction? Okay, this is the junction, right? This is the junction. And for this junction, we have to apply the junction rule. Then what is our junction rule? This is the junction. Now what is the entering current? I1. Entering current is I1. Leaving current is I2 and I3. Sum of currents entering equal to sum of currents leaving. That means we write I1 is equal to I2 plus I3. This is entering is I1 and leaving is I2 and I3. I1 is equal to I2 plus I3 we write. From Ohm's law we write I is V minus R, right? Potential difference by resistance. Potential difference by resistance. What is the potential difference at here? Okay, potential difference we will take here. Potential difference is from, we are traveling from here to here. The potential difference is high to low, high minus low we write. Current is always positive. Okay, current maybe negative we can take if you take the wrong direction. Okay, 20 minus V. Potential difference is the 20 minus V. By resistance is R1 and is equal to I2 we write as potential difference V minus phi. V minus phi by R2 we write. Here the potential difference I3 we write as V minus 0 by R3 we write. Okay. Now let us substitute all these values and simplify this. 20 minus V by R1 is what? R1 is 2 plus is equal to, not plus, V minus 5 by R2 is what? R2 is 4 plus V by R3. What is R3? R3 is 2. Okay. V minus 0 is V by R3. Now do the simplification. 20 minus V by 2 is equal to, LCM is 4 at here. Then V minus 5 plus 2V you will get. Then 2 2 cancel here. Then 2 comes to left side. 2 into 20 minus V is equal to, this V plus 2V, 3V minus 5 we will get. This is 40 minus 2V is equal to 3V minus 5 you will get. This 2V taken to left side, 5 to taken to right side. 40 plus 5 is equal to 3V plus 2V you will get. Then 45 is equal to 9V we will get. Then from this 9V is equal to 45. Then V is equal to 45 by 9. Sorry, this is 3V plus 2V is 5V only. 5V. That is 45 by 5. What you will get here? 9 volt we will get, right? That means potential at junction. Potential at junction is 9 volt. We find out the potential at the junction at here. At the junction the potential is 9 volt. Okay. What they are asking? If the switch S is closed, then what is the current passed through it? The current through switch we have to find out. Current through the switch S, that is I3. What is the formula for I3? Current is equal to potential difference. Potential difference what you will get? Here potential is V, here potential is 0. Then potential difference is V minus 0. Why here 0? It is grounded. Ground potential is 0. V minus 0 by R3 we write. Okay. You can also find the current through R1, right? 2 ohm. Potential difference 20 minus V by resistance 2, right? V value is we got 9 by R3 value we got as 2, 9 by 2 we got as 4.5 amperes. If you want to find out the current through R1, how to find out? Okay, current through R1, current through 2 ohm, this potential difference 20 minus I1 formula. I1 is the current through this. I1 we can find out, I2 we can find out, I3 we can find out because we know V, right? This is how to solve the problem. This is one problem based on based on Kirchhoff's first law. I will give one homework problem and I will close. Okay, this is our homework question. The question is that find the current through 12 ohm resistor in the figure. Okay, here 15 volt they gave, here 2 volt, here 3 volt, here 4 volt, here 6 ohm, 4 ohm, 2 ohm, 12 ohm, this one. Current through 12 ohm we have to find out. Here 15 volts, then current through this we have to find out. For example, this is 15, this is 2. Current starts from here and goes like this, 15 and 3, 15 and 4. That means current high potential to low potential it will goes. Current starts from the 15, like this I1 you take, I1 and this I1 will be split, this side I2, this side I3, this side I4. We write I1 is the entering current to this junction and leaving current is I2, I3, I4, right? I1 is equal to, we write as I2 plus I3 plus I4. And then we can apply the I1 formula. I1 is the potential difference. Here potential is 15, but here we don't know. That potential you can consider as V. Then potential difference 15 minus V by resistance I1. I2 is V minus 2 by resistance. Like this you can find out. And find out the current through 12 ohm. And compulsory you have to find, complete the solution. And today itself you have to write the comment about the lecture and about this answer. Okay, thank you for watching my lectures and continue to watch, and thank you. Till now, if you not subscribe my channel, subscribe and share to your friends, those who are in the class 12.